So let's look at solvent and how we choose mechanism then. So if I have a primary alkyl halide, it actually doesn't matter how good of a nucleophile we have. So if I have a strong nucleophile but it's solvated, like I would in this case, it doesn't make any difference. A primary alkyl halide is always following SN2. Likewise, if I have a tertiary alkyl halide, so here's my primary alkyl halide, here's my tertiary alkyl halide, it also doesn't matter what my nucleophile is because it's never going to go by SN2. The bromide's always going to leave first, or the halogen will always leave first. To make my carbocation, and then the nucleophile will add to give the final product. So where it matters is with a secondary alkyl halide. So if I have a secondary alkyl halide, now I have to look at whether or not I have a good nucleophile. Right? So the next question after I look at that halogen is I look at the nucleophile and I say, is this a strong nucleophile? And the answer is yes, it is a strong nucleophile. But then I have to keep going and say, okay, I look at my solvent now and say, is it solvated though? And this is a polar aprotic solvent, so it's not solvated, so the answer is no. So then, the third part of that question is it still a strong nucleophile? And this answer is yes, because it was a strong nucleophile that's not solvated. And since it's still a strong nucleophile, then it'll do an SN2. Cyanide comes in, bromide leaves. In the last case, I'll just do the same reaction. So we ask the same set of questions. So again, I have a secondary alkyl halide. I have a strong nucleophile. Yes. Is it solvated? And now I have ethanol as my solvent, so it's a polar protic solvent. So yes, it's solvated. So do I still have a strong nucleophile? The answer is no. And because of that, now it's limited to being an SN1 mechanism. Bromide leaves first. Giving us the carbocation intermediate. Then the cyanide enters. The last thing I want to look at in this chapter is the stereochemistry of nucleophilic substitution reactions. So let's first look at an SN2 type reaction and think about what happens in the mechanism, and then we'll try and see what the stereochemical outcome will be. So if I start with R2-bromobutane, and I react it with cyanide ion in some kind of a polar aprotic solvent. So if I start here, I have a secondary alkyl halide, so it can be SN1 or SN2. I have a good nucleophile, Cn-, and because it's in a polar aprotic solvent, it stays a good nucleophile, and so it follows an SN2 mechanism. So in an SN2 mechanism, remember the cyanide adds at the same time that the bromide leaves. And the important aspect of it is that the cyanide has to come in by what's called backside attack. Which really just means that the entering group, or in this case the nucleophile, must add opposite the leaving group. And actually the explanation for why this happens gets to molecular orbital theory. And so there's a molecular orbital here between that carbon and that bromine. This is the bonding molecular orbital. And that molecular orbital has 2 electrons in it, and it's lower energy. So if I'm going to draw it, I could draw the 2 atoms, carbon and bromine, come together in 2 possible ways to form a sigma bond. One way it's lower energy, and that is the electron density is between the carbon and the bromine nuclei. And this is called a bonding orbital. So this would be a sigma bond. And the other one is the antibonding orbital. So if my carbon and my bromine are here, all of the electron density of the orbital is outside of the 2 nuclei. And this would be called a sigma star, or a sigma antibonding orbital. Now, for any reactions to occur, there has to be an interaction between orbitals. So this orbital here has 2 electrons in it. This one's empty. So as my nucleophile comes by, Cn- is my nucleophile, it has a pair of electrons that it's going to be donating. So what it does is it needs to find an empty orbital. So this pair of electrons will find this empty orbital, so that's where it's going to add, and then this pair of electrons will start to break and go off onto the bromine. So that's why it has to come from backside attack, because that's where the sigma star, or the sigma antibonding orbital is. That's the empty orbital. And as this reaction occurs, this orbital will become the new bonding orbital. So the outcome of all that is that what we get is we get inversion of stereochemistry when we have reaction at the stereocenter. So if I'm going to draw the product of that, then instead of coming out of the plane of the board, the cyanide is going to go back into the plane. So this will be a reaction product. Inversion of stereochemistry. Now what happens with an SN1 reaction? So I'll just take the exact same reaction, and this time I'll do it in cyanide, but in a polar protic solvent, I'll do methanol. So now we start here, and I've got a secondary alkyl halide reacting with a good nucleophile cyanide, but the methanol, the polar protic solvent, makes it a poor nucleophile, and that makes it SN1 mechanism. So in SN1, the bromide leaves first. I'll draw in my proton that's at that position where the bromide was. So I get a carbocation there. Now if you remember the shape of a carbocation, carbocations are always trigonal planar because we have 3 electron groups. The 4th is empty, so that one doesn't repel. So we have 3 electron groups repelling, and with 3 electron groups repelling, the furthest they can get away is 120 degrees, or trigonal planar. Now when the cyanide comes in, you have 2 choices. The cyanide can either come in from the top of the molecule, or the cyanide can come in from the bottom of the molecule. Remember, it's flat. So there's no preference for the top or the bottom because either side is exactly the same, being that the molecule is flat. So if it comes in from the top, my cyanide group will be coming out of the plane, and if it comes in from the bottom, my cyanide group will be going back into the plane. So now think back to your stereochemistry chapter. What's the relationship between these 2 molecules? They're enantiomers. And what we end up getting is we get a 50-50 mixture of these 2 enantiomers. In the middle of this, we lose stereochemistry. We had stereochemistry at the start, we lose stereochemistry in the intermediate, and we gain stereochemistry back at the end. Once we've lost chirality in the middle, we no longer have a chiral product. We have a 50-50 mixture of enantiomers at the end. This is not optically active. And so what we call this is we call this a racemic mixture. And since this mechanism forms a racemic mixture, we say that the SN1 mechanism occurs with racemization of stereochemistry. While an SN2 occurs with inversion of stereochemistry.